Let's welcome our next speaker, Pavel Lougovski from Oak Ridge National Lab.
And I'm going to talk about the tiger. I don't know why. I can see it on the laptop, but is it? Oh, okay. All right. Well, first of all, let me thank the organizers for putting together a really great conference. At least to me, it was very instructive, and I've learned a lot of new things. And yesterday and today, and it's been great to talk to people about new ideas and stuff. So, but before I start talking about our results, I have two confessions to make. First of all, I'm a theorist. Don't hold this against me, and I'm going to talk about experimental results. But I find these days I find myself more and more running experiments that were built by other people remotely, but so it's interesting. And the second confession is that this is an integrated photonics conference, and I'm going to be presenting results that are bulk optics. So, anyways, so let me sort of give you a brief introduction how this work came about. So last year we had two interesting papers in PRL, and they were picked up by nice folks at Ars Technica and featured on their website. And so there were two independent works, not related. I was just fortunate to be part of both projects. And one of them was a work on quantum digital simulations using IBM and Rigetti quantum computers over the cloud. And that was the first time that we actually demonstrated an application of quantum computer, in particular quantum simulations, to the field of nuclear physics. So we've simulated the simplest nuclei possible, which is the deuteron. So it's an analog of molecular hydrogen, so it's proton and neutron. And the other work was completely unrelated, and it was based on our optics experiments and theory that we've done before that. Where we actually demonstrate for the first time, at least to my knowledge, that you can implement single qubit gates for frequency encoded qubits using linear optical devices. Well, so of course people before have recently, well before 3 years ago, have Gator's group, for example, have demonstrated that you can do those operations on frequency encoded qubits using nonlinear interactions, but this work was the first one where we actually done electro-optic modulation and pulse shaping, so no nonlinearities. And so it occurred to me that we can actually put those two together and use this versatile platform of frequency encoded qubits to do quantum simulations. And the reason for that is we've seen here in this work a very nice result where we can run many single qubit operations in parallel, and also with a very high fidelities that are compatible with the best hardware out there, Google's hardware and Traptime hardware, so we're in the same kind of realm of fidelity. And at the same time, what we've seen doing our cloud-based quantum computing is that it's hard to push problem sizes beyond 5-6 qubits, so we were stuck with a Hilbert space sizes here for simulations of about 16. If you try to push it past that number without sort of paying much attention to details, then all of a sudden the results made no sense. So we thought, like, well, okay, let's put these two together because we have really nice gates here, and maybe we can get something out of it. And indeed, we were able to push simulations for subatomic systems to where we were not been able to do it using, I will call it conventional superconducting cloud computing. Anyways, so that's the premise. And why are we interested in subatomic physics? Well, at the end of the day, it explains sort of our existence at the scale, at the grand scale of the universe, right? So to understand, say, neutron binary stars or mergers and violent astrophysical effects, you actually need to understand nuclear and subnuclear interaction really well. And so computationally, those are very hard systems to crack classically because they exhibit their fermionic systems with a lot of degrees of freedom, and they exhibits very strong correlations. And those are exactly the types of physical systems that quantum computers are envisioned to simulate better than classical computers. And so there is already, I mean, we're standing on the shoulders of giants here, of course, because there's been at least 30 years of computational efforts in classical HPC to simulate those subatomic systems. And there is a very well-defined computational program there. And of course, it's two-prong approach. One part of this approach is to sort of push as far as we can simulations of the lattice QCD systems, QCD being quantum chromodynamics. So quantum chromodynamics explains the strong force at the very fundamental level. It's a non-abelian gauge quantum field theory, and people have been able to treat from the first principles some simple nuclear structures like helium-4, for example, using lattice QCD calculations. But that's pretty much the extent. I mean, all these HPC systems that we have today are only able to push ab initio lattice QCD calculations to system size of helium-4. So it's a 4-particle nuclei. Okay. So 2 neutrons, 2 protons. And so on the other hand side, of course, if that was the only thing we could do, then we would be in a very bad shape, because we want to describe properties of very large, very heavy nuclei, right? So, for example, tin is an interesting one. I'm from Oak Ridge, so uranium used to be an interesting one to us as well. And so those systems where we are able to describe at some effective field theory level, so where we replace the full-blown lattice QCD calculations with an effective field theory that contains way less parameters, right? And so then we can treat those computationally in a classical computer. So the idea, computational idea here is, of course, inform parameters of effective field theories from lattice QCD calculations for smaller size calculations. So being able to predict those effective parameters really precisely, and then extend the reach of lattice QCD simulations via effective field theories on supercomputers using those really well calculated, very well known parameters, extend them to larger systems. And so that's where we hope that quantum computing will help. It will replace conventional computers in treating lattice QCD systems, but also EFT systems. And so that's sort of the premise. And so here's the 3 systems that we actually set on to simulate with photonics in this particular work. And this is the triton. So it's essentially a heavy hydrogen nuclei, right? So usually when you talk hydrogen, you talk about protons. So it's a single particle. But you can add 2 neutrons, and it's still a stable nuclei, and you get what is called the triton. So it's a 3-particle system, and of course, there is indeed a 3-body force here involved, so there is 3-body potential term. Unlike chemical systems where you can get away with describing everything in terms of pairwise Coulomb interaction, essentially. So this is really different from chemistry. So you have interaction potential that not only contains 2-particle term, but also 3-particle term. And so then the helium-3 is also a 3-body system here, but it's kind of flipped, right? You have 2 protons and 1 neutron. And fun fact, it's the only system that has more protons than neutrons and is stable, right? So all other stable nuclei have more neutrons than protons. And helium-4, or the alpha particle, is the 4-body system. And again, on top of the 3-body interaction terms, it actually does have a 4-body term in the interaction Hamiltonian as well. So they're quite different from chemistry. And if you were to try to simulate either one of those on a digital quantum computer, like IBM, using methods similar to chemistry, methods like VQE and unitary coupled cluster, you would find yourself running into problems fairly quickly because you have this 3-body terms and 4-body terms, and now you have to put them in the exponent, and it blows up into your face really quickly. All right, so that's the first thing. And then the other one, again, so this is again, we will be solving those problems at the level of effective field theory. So we'll have effective Hamiltonian, that is second quantized fermionic Hamiltonian, and then we'll try to find a ground state of it using our quantum frequency processor. Next system of interest is, well, I've declared that it would be interesting to go from sort of latticized quantum field theories to effective field theories, so inform effective, how you construct effective field theories from ab initio, so from first principles. And so we cannot quite do it for lattice QCD yet with our quantum computers or quantum simulators. So we've done for very, very watered down quantum field, latticized quantum field theory, which is Schwinger model. And for those of you who does not know what it is, I will explain quickly. The Schwinger model is essentially quantum electrodynamics in one dimension, okay? And we'll put that on the lattice. And so, of course, an interesting story about quantum electrodynamics in one dimension is that, well, you still have your electrons and positrons, you have your fermions, but the gauge field, of course, now is a scalar, so it's a billion gauge is scalar, and of course it's non-dynamic because in 1D you cannot have transversal condition here, right? So you cannot have propagating electromagnetic fields because it's a one-dimensional system. So it's non-dynamic gauge link. But because of that, it actually closely mimics some interesting effects that are traditionally observed in non-abelian gauge field theories like QCD, like strong confinement and all other things. So that's why it's interesting, and that's why people sort of find Schwinger model as prototypical sort of lattice QCD system, yes. And so what can be done is, again, we have to discretize the system. So this is a continuous Lagrangian for the continuous Schwinger model, and we want to discretize it in 1D, and so we end up with a Hamiltonian that looks like that. So there is something that resembles hopping here, and there is the Z terms. So it turns out it's still pretty non-trivial to simulate this type of models on a quantum computer. And so what we do is we basically laticize it. So we have at each spatial lattice, we have a one-dimensional spatial lattice with n sides. At each side we can have an electron and a positron, so they always come in pairs. And so there is a gauge link between lattice sides. Again, it's a static gauge link. And so what we're interested in is we're interested in populating this one-dimensional lattice with, say, with a charge and anti-charge, and populating them at different lattice spacing, and figuring out what is the effective interaction potential in that system. And that will be our effective field theory, essentially. So we have we've taken our lattice quantum field theory, and we've computed effective interaction potential between two static charges there, or charge and anti-charge, and then we don't have to use our quantum field theory anymore. We can get away with just simulating two charges and an effective potential. So that's sort of the big goal. But we need to know what that effective potential is. And so that's what we've done on a quantum computer, sort of figure that out for 2 and 3 charge systems. Okay. So those are the systems that we dealt with. And so in the near term, okay, we have to basically admit that in the near term we want to have fault tolerance, and so we cannot do arbitrary things with our quantum computers. So we have to look for those things that quantum computers can do the best in the near term and compete with classical computers. And one of those things is, for instance, calculating n-qubit observables and spin observables or things like that. So if you have an observable and you would like to compute an expectation value on a classical computer, so observable O, n-qubit observable. So if you want to compute an expectation value of that thing, it's pretty challenging classical computing test because your state vector is basically size 2 to the n, and your observable is a matrix that is 2 to the n times 2 to the n, so 2 to the 2n. And so the roughly number of operations is this. So if n is on the order of 50, there's not much you can do even with the exascale type computing systems. Okay. So and that's where quantum computers, even with 50 qubits, can come in handy, because they can compute those expectation values pretty much in their sleep. Okay. Of course, it takes, we know that quantum mechanics is sort of a probabilistic theory, so to compute an expectation value, you have to prepare a state psi m times, and sort of measure expectation value, you have to repeat your measurement m times and then collect the statistics and add it all together. But nonetheless, it can be done pretty efficiently these days. So that's the feature that we want to borrow for our algorithms. And in particular, the algorithm that we are interested in is variational ground state, is variational quantum eigensolver that has been used many times now in the last 10 years to compute ground states for various physical systems. So the observable of interest, of course, is the energy. There's a Hamiltonian, usually what people are interested in nuclear systems is the binding energy, for example, right? So it's the lowest energy of your Hamiltonian. And so the idea here is that, so in variational quantum eigensolver, it's an interesting idea, and it's been put forward by Alanis Purguzek's group at Harvard at the time. And in fact, an interesting fact is the first implementation was optical, right? So the Andrew White's group. For the hydrogen molecule. And so the idea is that, okay, so I will outsource computing expectation values to my quantum computer or whatever quantum device, not necessarily computer, not necessarily, actually that doesn't have to be a digital device, it can be an analog device, and that's what we exploit in our work. It's not really a digital device. But so the fact is that we have an observable of interest, which is a Hamiltonian, and would like to compute an expectation value of that thing on a quantum computer. So, well, we have a prescription for that, give or take. And so what we'll do is we'll prepare initial state, but we'll prepare initial state that can be parameterized with some linear number of parameters. So it's really tractable for classical computing. And then what we'll try to do is we'll try to compute expectation value and update our direction in the parameter space such that it minimizes the expectation value. So it's variational approach in its finest, and it's been known for at least 300 years. So, that's basically the theoretical basis for our work. And so now we'll try to implement it in what we call the quantum frequency processor, and I will quickly explain what it is. So, I don't want to claim that we invented the frequency encoding. It's been invented before us. People thought about encoding quantum information in discrete frequency beams. But so the idea is that basically you have two frequencies, omega 0 and omega 1, and if you have a single photon of frequency omega 0, then you can call it logical 0 state, and if you have a frequency omega 1, then you can call it logical 1 state. Okay, so simple enough. And this sort of coloring scheme is really drastic because we are working with a frequency difference of about 25 gigahertz, so that I don't think you will be able to discriminate the colors with your eye. Then, of course, we know that, and so we don't want to use nonlinear optics. We would like to use linear optics, and so there our options are limited. So it's like line-by-line pulse shaping, which I got introduced because Joe Lukens, who will actually speak about more details of the experimental work that we've been doing tomorrow, who came from Andy Weiner's group, who actually pretty much invented this thing back in the day. And so that's how I learned about it. And we said, like, well, we can use those devices to do quantum information processing. So that was interesting. And that's how our collaboration with Andy Weiner's group at Purdue was very fruitful here because they have enormous expertise there. And so pulse shapers is one component. So pulse shapers can apply arbitrary phase and actually amplitude to those lines, line by line. So that's nice. And another tool that we have is a phase modulation. So we have electro-optic phase modulators, right? So Okay. So electro-optic phase modulators act as sort of mode spreader. So you come in with a single tone signal, and the electro-optic modulator, depending on what your driving pulse is, spreads it across infinite number of sidebands, really. And so the idea in the quantum frequency processor, so the difficulty is to sort of stay confined to your qubit space, to logical qubit space, because electro-optic modulator will take you outside of it really quickly. It doesn't care about your logical qubit. It populates everything. And so the idea then is to leverage, of course, interference in the frequency domain if you want to sort of restrain yourself to operations in a logical qubit space. And that can be done. And we had a theory paper, Joe and I, back in 2017, how to use those building blocks and put a quantum frequency processor together. And you can actually do all the linear optical single and 2 qubit gates in this approach with exactly the same efficiencies as polarization or spatial encoding. But the nice thing is that if you can actually implement the same gate or different gates in parallel in this approach really easily. And this is not the feature that polarization or spatial encoding offers, really. And of course, there is interferometric stability because it's all single mode, right? We're talking about frequency encoding. We don't care about different spatial modes. We're all in the same spatial mode. And so Joe will talk more about all this nice experimental work that we've done and theory that we've done in that regard. So, but for this particular project, we had to be inventive because we were doing sort of an analog simulation. And so what we've done is we took our systems have a second quantized sort of fermionic Hamiltonians that we had to simulate or find the ground state of. And so we couldn't do it sort of circuit style. So what we've done is we used the trick of projecting those second quantized Hamiltonian on space, on Hilbert space of good quantum numbers, which is always possible. And in our case, it was parity momentum tall spin quantum numbers. And so now we are dealing with very large matrix, but this matrix has some sort of direct sum structure. So we'll have sub-blocks that are not talking to each other, and they're much smaller in size. And now we can actually diagonalize each sub-block individually and then look which one has the lowest energy, and that's going to be our ground state. So that's the idea. And then once you have the structure in place, if you look at it, you can map it on a single particle. You can treat it as a single particle problem, and if you look at the Hamiltonian, it looks exactly like a multi-port interferometer Hamiltonian, and that's where the light bulb went off, and so like, okay, well, so we can actually measure energy using, because quantum frequency processor is really good like any other optical system at preparing this, at having those controlled multi-port interferometers, and so the only remaining issue is to prepare a variational wave function, and in this case, again, as I said, since it's a single particle problem, effectively we can get away with preparing a variational function that is a single photon over n modes, with some coefficients, which defined by the number of variational parameters you have. And so the rest is pretty much it's trivial, or if you have good grad students and good employees. So the one thing that I wanted to point out also that if you're dealing with a single photon wave function, so variational approaches are the same as if you were to deal with coherent states actually. So there is no difference if you're using variational algorithm, whether you're using truly single photons or coherent states. The only difference in the visibility picture that you're making is just the amplitude of visibility fringe, and that will be related to the amplitude of your coherent state. And that's what we actually used. So instead of, and then if you're using coherent states, then you can reduce your statistical noise quite a bit. And we've been able to demonstrate that even for the largest of the system that we simulated, helium-4, which was essentially a 64-dimensional Hilbert space, we were able to variationally recover the ground state to within 3% of what the true value was. So, again, we've done the same thing using our quantum frequency processor for producing this effective interaction potential for the Schringer model, and so this is repulsive and attractive two-particle interaction for a four-spatial site. Schringer models, so those points are all experimental, and there is some uncertainty propagation that we've done. And so this is on the archive. Please take a look if you have time. I think it's an interesting work. And so this is this work wouldn't be possible if not all this fine folks all across the country, and especially Andy Weiner's group. And I'm really looking forward. The reason why I'm here is because in the last 6 months we were fortunate to start talking with AFRL, Mike Fanto, Matt Smith, and Stefan Prebel's group, and Dirk Englund's group about integration. And so we actually have an integrated version of our setup coming online sometime soon. And we are really, really excited to test it out and see what we can do with that, because loss has been a big problem in our case with bulk elements. And of course, I should not forget to mention, this also wouldn't be possible if not DOE Office of Science, Office of Advanced Scientific Computing. So I'm fortunate to lead CAD and QCAD projects at ORNL, and of course internal funding from the Oak Ridge National Laboratory. And here's the beautiful Smokies, and we have jobs, so I'll put it out there if you're interested in coming at all levels. Thank you.
We have time for some questions.
I think we need coffee, right?
We got one more before coffee. All right, well, if there aren't any questions, we'll thank Pavel again.